Welcome. Welcome to our Kolot Kehilla presentation. This morning, Adrian and I have come up with a brunch menu that we wish we could share with you in person, but you'll have to be satisfied with the video link. These recipes can be found as a link from the announcement, which was emailed to you. So for those who would want to be able to make any of these recipes, they are available. Sometimes, however, we modify them as we try them for the second, third, or fourth time before the presentation. Where we have, I will try to clue you in. The first thing we have this morning, and this is Adrian's because she's the baker, I don't bake worth a damn, is an artisanal bread, which is a sourdough bread common to the northern Italian Piedmont area.
Made with sourdough.
We've used this very good sourdough bread to make a bruschetta pomodoro, that is bruschetta with tomatoes, as well as a crostini bianchi, a white crostini, which is a ricotta cheese and anchovy spread. We also have pomodoro con tonno, which is tuna stuffed tomatoes, garnished with some pimento, and as well as pomodoro ripiene con formaggio, which is a goat cheese stuffed tomato with spinach and chives. For a salad, we have insalata di melanzana con pepperoni e cetriolo. Please excuse my bad Italian. Roasted eggplant salad with peppers and cucumbers. We have something special today. It's an Italian specialty, but it has a long history at Beth Israel Center. Back in the 70s, when Mrs. Scher supervised the kitchen and had her staff of Italian ladies who cooked, they used to make on a regular basis marinated mushrooms, which were marinated overnight in wishbone Italian dressing or a vinaigrette of your choice. Hence our mushrooms today. For our pasta choices, we have gnocchi made with mashed potatoes and spinach. We have polenta grassa, which is a baked polenta. We've used a finely ground polenta, which makes it reminiscent of grits, but it's also very interestingly made with a coarser ground polenta. And it's really a polenta lasagna with layers of fontina cheese between the layers of polenta. For those of you who like risotto, we've made our first attempt at a fish risotto con pesca, which is a risotto with shallots, white wine, and scrod. For our fish course, we have sogliola con bagnette, which is baked sole, and this is baked with breadcrumbs and rolled up, served with what they call a bagnette, which is a Piedmontese green dressing, often served on boiled fish or boiled vegetables. This is parsley, breadcrumbs and vinegar primarily. For dessert, and it's very appropriate for our explosions in the universe talk, is a bomba cake. A bomba di mandorla alla veneziana, which is a Venetian almond cake studded with almonds and dried fruit, which has been soaked in rum, which differs a bit from your recipe, which was posted. But this is supposed to represent a cannonball with shrapnel, and it's surrounded by little hand grenades that we made on the side. This is our menu for this morning. You're welcome to try any of the recipes you'd like. We're never satisfied. We always try something different every time we make it. But these are all enjoyable to eat. Thank you for your attention.
Barry, it is and Adrian, it's mouth-wateringly delicious looking. And you got a thumbs up from Marina as soon as she saw the bomba cake.
Yes. No, even before.
So Barry, as soon as you're ready, you can introduce our featured guest and speaker, Marina Orio.
It's my great pleasure to introduce the speaker for this morning, a sometime member of the congregation who travels widely about the world, searching for the origins of our universe and to answer various mysterious questions. It's a particular interest to me because almost 60 years ago, I was looking at gamma ray emissions on a gamma ray camera, primitive gamma ray camera, which was in the OGO-A, the Orbiting Geophysical Observatory, one of the early satellites launched by the United States for scientific research. Much more sophisticated methods for analyzing our universe and searching for what's happened in 13 billion years is being undertaken today. And Marina Orio is one of the significant leading investigators of attempting to answer these questions. She was born in Fabriano, which is in north central Italy, in the Ancona region. She received degrees from University of Padova. Now, for those of you who don't know where Padova is in Italy, remember your Shakespeare, and remember this is what we call Padua. So she comes to us today from the National Institute for Astrophysics at the University of Padova. She also is a visiting scientist in Israel and has been a visiting scientist at the University of Wisconsin since 1993. She was one of the first people my wife and I met when we came to Beth Israel, and we've enjoyed her conversation many a morning. Thank you for all coming today, and now on to Marina and her talk.
Yeah, sound appears to still be off if you don't realize.
So, first of all, we have all the electromagnetic spectrum at our disposal. And as this slide shows, we do have a very, very wide range. This is a logarithmic scale. And all of us are familiar with the idea that radio waves have a length the size of a house or more. When we go to X-rays or gamma rays, we go to the size of a molecule or an atom. And the frequency, of course, is inversely proportional goes in the other direction. And we're all familiar with the concept of frequency from hearing radio broadcasts. Energy is proportional to the frequency, and we usually can measure it in different units. And these units here, the electron volt, translate also in units of temperature. What happens is, however, that some of these wavelengths can only be observed, some of these energy bands can only be observed from space and not from the ground. It's quite amazing that in a logarithmic scale, the optical, the visual band is so small, so narrow, and this is the range in which we perceive the world. Instead, there is a much larger wavelength of radio waves, and we were not made to perceive radio waves with our body, with our senses, unless we use an instrument to translate the signal into an electromagnetic signal and then on sound. It's amazing that most of these wavelengths, however, are blocked by the atmosphere. So we need to go to space, and of course, this is all very modern. So unless we observe radio waves, we have problems with infrared, but in infrared we can really observe some energy bands from mountains or from high up in the atmosphere. When we go to gamma rays, X-rays, ultraviolet, we have a problem, of course, and even for the longer radio waves. So we need space missions for those. Now, it's amazing to think that during the scientific revolution, in only 200 years, people were able to understand that the universe could be perceived, everything could be perceived in all sorts of energy bands, and that there wasn't only visual light. It all started in the 1800s with diffraction prisms, and on one side, so there was something in some experiment with William Herschel, a famous astronomer who actually worked also with a woman, with his sister. All his family was doing astronomy. They found that something hot had different lines when you passed it through a diffraction prism that couldn't be actually perceived by the eye, by the human eye. And then from looking at the light from a chemical reaction, Ritter in 1801 found out that there was ultraviolet light. So at this point, they knew that there were some bands close, the near infrared and the near UV, ultraviolet, that were very close to optical light and couldn't be perceived by our eyes. But it took until Maxwell's theory of electromagnetic radiation and experiments done around it in 1886, Henry Hertz was able to detect radio waves. At that point, of course, the radio later was developed, but it took another 50 years, almost 50 years, to really understand and to hear radio waves from the universe. Then there was all the research on radioactive substances and X-rays. So this is Herschel. This is Ritter, Hertz, Röntgen, and Kehilla, who discovered X-rays. So during this research on radioactive substances, of course, there is also a very famous woman. These are all men. There were very few women at that time working in science, and they were all mostly working with relatives, or they were from rich families who could afford certain sort of expensive pastime. So they were already women since the beginning of the scientific revolution and before. However, we remember mainly the men, except one woman who paved the way for women to become a role model, and that was Marie Curie. So in 1895, by studying fluorescence, Röntgen discovered X-rays. They didn't have any idea how dangerous it was. Röntgen, Marie Curie, Becquerel, and lots of less famous people all died of cancer. Even when I was born in 1959, it was known that X-rays were dangerous, but it wasn't clear how dangerous they were and what ratio, how much X-rays we could tolerate. I was a breech, I was a head breech, it was kind of dangerous. There was a very good midwife, a very, very experienced midwife who took me out without a C-section, but they gave her the X-rays of the fetus before I was born. It would have been extremely dangerous. Other babies like me died in the first year or two after birth because of the dose of radiation. I survived. After that, Marie Curie actually received the Nobel Prize twice for physics and for chemistry in 1803 and in 1903 and 1911. One for the discovery of radioactive activity, and one for the discovery of radium. And she was a real genius. She and Einstein were just people of unbelievable depth and intelligence. And it's quite amazing to think of how their brain worked and what they were able to do. So it took a really genius woman to pave the way for women to go into studying physics and chemistry. So Paul Villard, studying radium, discovered gamma rays. And so we have all the whole range of electromagnetic radiation at this point. When we look in infrared, we see through this dark space. Many people have asked me, why did the James Webb, why was it decided that the James Webb would observe in the infrared range? So when there is something that is called cosmic dust, namely grains of molecules, small grains of molecules, and from there stars are formed. When that happens, when you have a cloud of cosmic dust, in the visual and in the UV or in the near X-rays, it can be completely black. It's not penetrated by light. If we look at this image in the infrared, it looks completely normal instead. In radio astronomy, we see actually, even if the energy range is considered low energy, we actually observe phenomena that can be very energetic because we observe synchrotron radiation that is due to charged particles moving at relativistic velocity parallel to magnetic fields. And they usually originate in very energetic phenomena. So we observe radio waves from pulsars, which are spinning neutron stars. They have a very precise clock spinning at very, very high frequency. And then we observe at different wavelengths, we observe gas. There is molecular gas, and especially important is the 21 centimeter hydrogen line. So this is a line that is due to a transition in neutral hydrogen. It is common in space, and it gives us the map of the gas in a galaxy and in the universe. So it's very important because some galaxies are actually composed mainly of gas, and from gas we form stars. In microwaves, at the temperature corresponding, at an energy corresponding to 2.73 K, you observe the cosmic background, so the fossil radiation of the Big Bang. When the Big Bang started, the universe was transparent to radiation. It was completely opaque. There was no light emitted. So It took about 380,000 years for the radiation to be emitted, and it cooled. It was about 3,000 K. When I say K, these are centigrade degrees, starting so the absolute scale, starting from the very, very low temperature, the absolute zero, at which particles do not move anymore. So it's a centigrade scale, a little bit different from the usual one, but it's used in science. So this was the first irradiation of the Big Bang. It cooled and we can detect it, and we look actually for anisotropies, but they're very, very hard to find. It looks pretty homogeneous. In the infrared, where the James Webb Telescope, so famous these days, observes, in addition to cosmic dust and star formation, we see whatever is behind the dust. This can be done at slightly different wavelengths. And we can see very far objects, like very far away galaxies that penetrate, whose light in infrared penetrates all the dust or gas that may be in the way. Then there is a phenomenon called redshift. I think those of you who are in science know what it is. Maybe some of us need a reminder. When you hear like a siren, like an ambulance coming close to you and getting far, you hear a different frequency, the sound changes. So that's because the velocity, the frequency changes, and that depends on the distance of the object that emits the waves. The same is true for optical, for electromagnetic waves. And since the universe expands at very large distances, the main velocity, the main motion is that of galaxies expanding, getting far away from each other. And when we have a spectrum, usually an optical spectrum or any spectrum where we have lines of atomic transitions that we know very well which wavelength they should happen, we can measure the displacement and understand the distance. So we can, because of this redshift phenomenon, actually the light of the farthest galaxies that come to us is actually optical light that is redshifted, or we can even have, for the farthest object, I'm told that we hope to be able to eventually see UV, ultraviolet light. So, in optical, we see, concerning explosive phenomena, we see novel, supernova, no stars, or we need also optical light. Now, in the UV, we see the hottest stars. So now a star is a ball of gas with nuclear reactions in its nucleus. And hot, massive stars, more massive, the heavier a star is, the hotter it is. Because it has faster nuclear reactions. And also it is shorter lived. So they are associated with regional star formation, because when star formation has happened a long time ago, the stars, massive stars have already exploded in supernovae. All ordinary stars, like in UV and optical, all ordinary stars emit all these wavelengths, but we also see in X-rays explosions of compact objects in binary stars. We see a lot of binary systems that get so close to each other that matter is sucked, it is gravitationally attracted by the companion, and then, especially if the companion is already a very compact star, they will say what it is, what a compact star is, we can see a very hot material that emits X-rays, and then there are all sorts of instabilities and explosive phenomena that can happen. You can see also the tidal disruption of stars in the galactic centers when they're attracted by the huge, massive black holes that are at the center of galaxies. In gamma rays, we observe explosions of a rare type of supernovae. We observe coalescing neutron stars, all explosive phenomena. Shocks in mass outflows from these explosions, and we observe the most active galactic black holes. So very energetic and rather unusual phenomenon. So this is how the center of the galaxy would appear. This is from a textbook. They said the lane at the center of our galaxy appears. It has been reconstructed with smaller images, of course. So we can see dust and gas and molecules at the different wavelengths. We see in the visible light, optical light, we see reflected radiation of stars. In the infrared close to optical, But in visible light, we see a black line where all the dust that is formed, where stars are formed is. In X-rays, we see some very, very hot bubbles that only recently been discovered. And in gamma rays, we see emission from the collisions of cosmic rays that come from very, very far away. These particles that come from very far distances with atomic nuclei in interstellar clouds. This is one of the closest galaxies to us, the galaxy of Andromeda, M31. And the X-ray picture has been completed, but it shows mainly active energetic point sources, stars, binary systems. In UV, you see lots of all the massive stars. In visible light, you see all the medium-sized stars, mainly, but all sorts of stars. Of course, we can go deep, we can observe from Earth with big telescopes. In the infrared, you start seeing all the gas, different wavelengths, and radio too, and all the dust that is forming stars, and that is along spiral arms. Our galaxy is also made like that. Then there is a new field that has been developing in the last 50 years or so. It is called astroparticle physics. Through particles, we can detect either the highest energy gamma rays or neutrinos. We don't detect them directly. One way of detecting them, by the way, gamma rays have a large energy range, so many gamma rays are detected from space, but the highest energy ones are detected actually from Earth. There is an effect that is called the Cherenkov effect. When a charged particle moves in a medium, that can be air or water or ice, at a speed larger than the speed of light. Like in water, I'm talking in kilometers here, I can't translate in miles, but the speed of light is about 300,000 kilometers, and it's only about 200,000 kilometers in water. But a particle in a medium, not in vacuum, can move at a higher velocity than the speed of light. And what happens is an effect that has been discovered already, I think early in the 20th century, of light emission of these particles. These particles are actually usually electrons or muons that are similar in some ways. In the world of particle physics, 2 electrons. So through this optical light, we can trace either neutrinos or the most energetic gamma rays. Because they cause these reactions when gamma rays, when they hit the upper atmosphere, start causing the emission of electrons and muons. And we see them in optical light. One way of detecting them is through arrays of optical telescopes. These optical telescopes are made, like you've seen probably the James Webb, with small cells or smaller mirrors. The first idea of these mirrors was actually invented by a Jewish Italian astronomer, Guido Arturo. It took many years until it was adopted for all telescopes. And so it's done through interferometry. Interferometry means that when we have a signal coming from 2 different spots, the resolution, the angular resolution is proportional to the distance and inversely proportional to the wave. So what happens is that you can get much better resolution because these particles, these showers of particles, and then the optical light is very diffuse. It's very hard to know where they come from space. So with these arrays, and the different sizes are made to detect the different wavelengths. So supernovae have been known for a very long time, and there are 2 types of explosions, different types of explosions of massive stars or less massive stars. But the ones of massive stars have been always studied. But there are 2 types that can be observed only with these astroparticle physics methods. One is that some of the most massive stars that have been stripped by the outer layers have very energetic explosions when the central core of the star collapses, and they emit a lot of gamma ray light. So those are Barry was talking about that, and not only he detected them, but lots of military satellites, available satellites, were observing the Earth in order to detect nuclear experiments by foreign powers, Russians and others. And so despite the satellites started discovering every day one or more or several of these gamma ray bursters, and they coming from the sky. And so eventually it became a subject for astronomers, and it was much later discovered that many of them were explosions of not of nuclear weapons on Earth, but of this type of stars. Then another type of massive stars that have a collapse of the core, that are even more common, do not emit gamma rays, but emit lots and lots of neutrinos. More than 90% of their energy goes in neutrinos. So neutrino is a non-charged particle, it's very light, and it can travel from huge distances because it doesn't have a charge. It is not deflected by magnetic fields. In principle, we could see neutrinos from the beginning of the universe. That's why they're important in astronomy. So 35 years ago, on February 23rd, 1987, there was an occasion of a supernova near us that revealed many mysteries. Some of them we haven't solved yet. So this is an explicit image, I think in optical light, of the Hubble Space Telescope, where you see at light distances they form these rings of light. This seems to be ionized material that had been previously emitted, because of it is there. And this is the shadow of the supernova, the material expanding. These are not on the same plane, and how they are formed is not completely clear. In any case, because the supernova was nearby, with huge tanks of water with the photomultipliers that measured, that amplify the optical light, it was possible to detect the flux of neutrinos and prove the theory and understand exactly how they explode. So it was a big, I don't know how many of you remember reading that in newspapers, but it was a very big discovery that proved many things of stellar evolution. Before that, neutrinos had been detected from the sun, allowing to gauge the details of stellar models and stellar evolution. So Madison is very active in neutrino research from cosmic neutrinos, because we have here the headquarters of IceCube, a huge experiment of the United States in the South Pole, but with the international collaboration from all over the world, not just the United States. Most of these facilities I'm going to talk about today are very, very international. It's not possible just for scientists in one country to raise enough money to build or to have even the expertise to build one of these facilities. So the ones in the South Pole are not necessarily for supernovae, but they're aimed at a variety of phenomena, including the origin of cosmic rays and the eruption of giant black holes, galactic nuclei, all sorts of. So these eruptions would be due either to accretion or to merging of black holes. In any case, it has many scopes. And there was a person here who was the expert in building these photomultipliers detectors in ice. So it's a very Madisonian experiment with hundreds, with 1,000 people from all over the world. The other thing that made the news recently are the gravitational wave detectors. So gravitational wave originates from the dramatic merging of black holes or neutron stars. It originates in many other ways, but this is the type, the frequency that we are able to detect on Earth. So Rainer Weiss, an elderly gentleman who dedicated all his life to this, was able to build this amazing instrument, this amazing facility. He was the son of Jewish German refugees that came at the last possible time to save themselves from Nazi Germany. And you never know what these refugee children are able to do when they grow up. So he used for this facility. It's called LIGO in the United States, and it needs, in order to really make meaningful detections, it needed a similar experiment placed in Italy in order to be able to sort of understand where the signal came from in the sky. And there are going to be other similar interferometers and similar detectors. One is starting in Japan, there will be one in India, so we will be able to do some kind of triangulation and discover better where the signal comes from. In order to observe these explosions, also at different wavelengths, at electromagnetic wavelengths. This has been possible only one case so far. So the two US instruments are placed in the Hartford, Washington, and Baton Rouge, Louisiana, and they can measure 1 part in a million of a billion of a meter. So it is equivalent to measuring the distance to our nearest star, which is 100,000 million kilometers or miles, with an accuracy smaller than the width of a human hair. So having multiple interferometers, you can start locating the source in the sky because you just detect a signal from a portion of the sky. The way it is done, it's because of general relativity. It is another proof of general relativity. If we Einstein's theory is proved again and again to be true. So what happens is that you shine a laser, and now we have to think in 4 dimensions. So the distortion of these mirrors that reflect the laser are in 3 dimensions. So you can become fatter and smaller, but then you also have to calculate it with the 4th dimension, which is time. So the bottom line is that the laser is reflecting, and when there is gravitational wave, the two mirrors that reflect it are not the same anymore. One is perturbed, they're both perturbed, and so you will have the waves are not in phase anymore. And in this way, you can understand that there has been a signal of gravitational waves. So this is an impossible enterprise that became possible because even a truck at many miles of distance can perturb the instrument. So the way it was done from the engineering side is just amazing. So we had 4 Nobel Prizes related to astronomy and in all the history of astronomy until 2011. From 2011 to now, practically every 2 years, there has been a Nobel Prize for physics in astrophysics, given to for discoveries related to astronomy. So these are the 3 people who obtained the Nobel Prize for Physics 2017. So most of the Nobel Prize winners are actually men, but there has been in the last one in 2020, there has been finally a woman sharing the Nobel Prize. So Rainer Weiss is the person who built the experiment. Kip Thorne is a theoretician who knows the theory of general relativity so well that he could predict that it could be done. And Barry Barish was the person who put it all together and who made this huge collaboration with people all over the world. Many were in Italy, in France, and they were all over the United States, and there were foreign collaborations as well. So he made it work. He's like the manager, but it's not a trivial job to be a scientific manager of such a large collaboration with such delicate instrumentation. So I met Rainer Weiss. So astronomy is a small field, and when I started, it was much smaller. We had, I practically met everybody famous in astronomy when I was young. And over the years, all these people who got the Nobel Prize that were alive, I could actually either hear the lectures or talk to them directly. And sometimes it has been very inspiring, like in the case of Rainer Weiss. So I met him in Seattle, where I was visiting my son. I volunteered to give a talk at the Department of Astronomy, and he was giving a popular lecture that night. So he came over to astronomy and physics, and he said, I would like to talk with the scientists here. I would like to meet people, and can I give a talk? And they said, I was there when they said, oh, no, there's this lady, Marina Orio, who's giving a talk. You're not, she already took the slot for today. We don't have any more rooms. So I felt like I'm going to faint. What is he going to think? I had to take the spot of a Nobel Prize. He had just got the Nobel Prize a month earlier. So I was like, oh my God. But he was very kind and very generous, and he laughed and said, okay, so I just meet you all guys for coffee. The coffee room, they tell you about my science, and we discuss a little bit after Marina's talk. I came to the coffee, and he was so enthusiastic, and he was over 80 years old. I think he was already 83 or something. And he was so kind and so inspiring, and he loved to talk about science and what he had done. And it's really people like that. Not everybody's like that. Some people are very competitive and jealous of the research, and that's sometimes natural, sometimes it's exaggerated. But some people are really very inspiring, very such a pleasure to meet them. So the intelligence is they're so bright. So there have been two surprising discoveries through gravitational waves. What have we been able to detect is actually the coalescence of two black holes, and most of them are more massive than it was thought that stellar black holes could be. It's difficult to form very, very massive black holes because we need to have mainly only hydrogen and helium and not other elements in order to have a massive star form. The black hole mass comes from after a supernova explosion and a collapse of the internal core that has had nuclear burning, and it happens on the massive stars, and the mass of the black hole is proportional to the initial mass of the star. So it has to do a lot with stellar evolution and star formation. So if a neutron star is, if there is a merging of two neutron stars, if there is a merging of two black holes, we cannot really, is there a problem or can you see them? So if there is a merging of two neutron stars, you can actually detect electromagnetic radiation at all wavelengths. And then there was an alert sent to all satellites and to all astronomers. And well, not all astronomers, those that had subscribed for it. And it was detected in space, in gamma rays. So the location was narrowed down. And then there were some very clever people who have studied automatic methods on how to choose the galaxies to observe first to see if there was an explosion. What characteristics they would have in terms of star formation, ultraviolet light, and so on. And they were able to pin it down and find the explosion in optical light and get a spectrum. And then it was, that solved the puzzle because all the heavier elements are only formed by capturing neutrons, and they were not, in the Big Bang, only the lighter elements were formed, very, very light elements. The rest is more formed in star. And when you go to elements as heavy as gold or platinum, you need a very massive star because you need neutrons to make them, to be captured to make the nuclei heavier. And a neutron also decays in a proton and an electron and a neutrino. And so you can actually, and the photon, so you can actually get protons as well in this way. Now, so it was understood that they can be formed only in the most massive stars, and there was a whole theory of nucleosynthesis, as we call it, in the most massive stars. In supernovae. But actually, it was found that it's not possible to form some of these heavier elements. So the question is how to do it. And by looking at some signature in the optical spectra for these two neutron stars coalescing, we could actually realize that it happens when there is the coalescence, the merging of two neutron stars that attract each other because of gravitational radiation and start orbiting around each other until there is a boom. This sort of explosion that lasts maybe only for hours or less, so you have to be very quick to look for the electromagnetic radiation because that may also go down quickly. So astronomers advertised it by saying that through the Lago Virgo optical telescopes, they had discovered the origin of gold and platinum findings. So that was in the headlines in the newspapers, discovery of how gold is formed. So these are the masses. So the theory of relativity allows to predict with extreme precision by knowing the frequency that is detected, the time of the event lasts, and the intensity of the signal. You can actually, there is a relatively simple formula that gives you the masses of these two stars coalescing, merging. And so with electromagnetic radiation, the stellar mass black holes, there are also hugely massive black holes in the center of galaxies. I'm not talking about that. I'm talking about the black holes that are formed after a supernova explosion. So it was found that there are many more massive black holes than we thought. So that's one of the mysteries I was talking about. Neutron stars are more difficult to detect from Earth. There was one case and possibly another case, one of a neutron star and black hole. But a lot about stellar evolution is actually learned from these detections. And now we'll be able to have many, many more, to have really clear statistics of these extremely massive objects and how they merge. I have to say that half of the stars, and especially more massive ones, are in binary systems. And that's why some of them can actually eventually attract each other and merge. So, the future of gravitational astronomy is actually in space. So the European Space Agency, with some collaboration also with the United States and other countries, is going to have such an interferometer, not with a 2.5 miles distance, but with a huge distance between the lasers in space, with satellites in space. And they already made an experiment to find out whether this was possible by sending satellites and trying to shine a laser and see what happens. So in this way, in one way, we'll be able to detect a whole range of frequencies and much lower intensity and much a different wavelength of gravitational waves, and we'll be able to observe things like coalescing white dwarfs. White dwarfs, we'll talk about these in a minute, but they're the result of dead stars that are much more common than neutron stars or black holes. And we'll be able even to measure the signal while they're getting closer to each other, not necessarily in an explosion. And we'll be able to, so this will be relevant, as I will explain now, to the precursors of so-called supernova. And we'll be able to measure, this is an artist image, it's a two huge black holes of 10,000 times the mass of the sun or more that are coalescing. That happens too, and that's the only type of explosion that happens in the center of galaxies. One type of explosions I'm working on has actually to do with white dwarfs, and it's one of the main topics of research. And it's the stellar explosions are called novae. They've been observed for a very long time. They emit at all wavelengths. People in medicine are trying to determine whether they will also emit neutrinos, maybe. So they emit radio radiation, gamma rays, even the highest energy gamma rays. That's because a star gives material. The material is pulled from a star that can be a small star, like during the regular burning in the core, or can be a star that has already expanded, like in this example, has already expanded its envelope because it's between different types of burning in the core, and at the moment it becomes very large interventions and red. It's called the red giant. It doesn't have to be a red giant, it can be any star, and it will make there will be a disk that shines in UV X-ray that is very hot, especially close to the central launch. But in reality, we don't observe anything like this exactly. We cannot image because these systems, because they're quite far, so we don't obtain an image, but we detect them through different methods. On a larger scale, when we look at this object, we see very messy and difficult things to explain. This is one of them that has actually a red giant like in this picture. And you can see these are X-rays, and so this is a composite of X-rays and optical light in red. And they come, so there was material emitted by a nova explosion long time ago, I think, and it collided with some other gas that was emitted before, and you can see the X-ray light that is emitted. So, but these things are not, there are many mysteries still to explain. This is a picture I took at the Wind Telescope, one of the telescopes of the University of Wisconsin. And it is, there was a nova here in 1992 at this, someplace here. And it, so this is on a large scale. This is not the material that is active. What happens with a nova is that white dwarfs are more dense and compact if they're heavier, and when material is accreted, it can become explosive and it can ignite thermonuclear burning. In a white dwarf, you will have something like a metal. You will only have ions and metals moving freely. And in this state of matter, when you ignite thermonuclear burning, this is for nova, it's only on the surface. What happens is that you will be sensitive only to density, so the rate will start increasing and increasing, especially if the white dwarf is massive. And eventually, you can have an explosion. So this is a material that has been ionized. It's gas that was present in the stellar medium from which stars are formed. It was, it's sort of traced by the explosion of the nova. So some examples of how we use stellar explosions to actually explore a variety of phenomena. So one thing we always look for is the chemistry, the formation of elements in the universe. And nova produce several elements. They are not the main contributors to nucleosynthesis, but when there is an explosion like that, the white dwarf ejects the material that was accreted on top because of nuclear burning, you can form two elements that can be relevant for other fields. One of them is lithium. Lithium is a light element that is only formed in the Big Bang. So it's a mystery that it's destroying stars, and yet we have many types of stars, and yet we have many, much more lithium than we expected by measuring optical spectral stars. And what's the reason? So it was important to understand whether how much is formed, for instance, by novae, or by the few objects that can form it, because in this way we have the sort of cosmological budget of primordial elements, and we can gauge the Big Bang. So it all ties up to cosmology, to the origin of the universe. Another element that is really relevant for other fields is aluminum, because part of it is in a radioactive isotope that lasts for about 100 years. So if you have a protostellar disk near, when you form around the star, you have a disk from which planets are formed. If there has been a nova nearby, our prediction is that you won't have water. So that's, we're studying the conditions for the beginning of life, and that's probably a region in which you should look for signatures of life, perhaps, if you're dependent on water. So because these white dwarfs can be so massive, when they accrete mass, they can become heavier. And also there is a possibility of a merger of white dwarfs. So white dwarfs are very common because they're the remnant of what is left over by not very massive stars. They don't have an explosion, they just lose in sort of in the external layers. And they collapse because they cannot sustain neutral burning anymore. Because once you get to a peak that is called the iron peak, once you form iron, you cannot really produce energy in the core of stars as a nuclear reaction. It does the new reactions. So you cannot just heat the interior when the core collapses. And these thermonuclear supernova, they're optical light. So in some, maybe in some nova, or in any case, in some cases of binary white dwarfs, it's enough, that it's a few percent. you can have eventually a thermonuclear supernova. So there is a lot of nickel that decays into cobalt as a radioactive decay, and then in iron. This supernova form all the irons that we see in the universe. And the more nickel they have to, and cobalt they have to start with, the more luminous they are and the longer they last. So we can sort of gauge, this is how they put them all together in the same, this is light practically, so what we measure is equal to magnitude, it's a sort of rhythmic scale in days, in time. So you can sort of stretch them to the same scale depending on the peak luminosity, and you can understand how far they are. So they're used as indicators, main indicator of cosmological distances, very large distances. So I mentioned that there is something called the redshift, and that's why the Nobel Prize was assigned in 2011, because it was found out that the distances measured with the redshift did not correspond to the distances discovered by these standard candles that are these supernovae. Something is accelerating the universe of expansion. We don't know what. We call it dark energy, but it is a very powerful component of the universe. And so whenever one of these huge explosions is triggered, we think that we know fairly well how to determine. Actually, I wrote here a few things about the fact that actually they would collapse into neutron star, and there is only a narrow range, not so common. There is only a narrow range of density which you trigger the thermonuclear reaction of carbon that gives the explosion. So type 1a supernova are not really very common because either white dwarfs are not heavy enough to trigger this reaction, or they could become neutron stars. But there are, we observe them, and we use them as indicators of distances. So something is accelerating the expansion of the universe, and we have to find out why. Finally, the last thing I want to say is that we soon have the greatest movie of all time through a telescope that is being built in Chile, the United States. It's called the Rudin Observatory. So Rudin never got a Nobel Prize. She discovered what is called dark matter, a large part of the matter that we observe by looking at how galaxies rotate, and maybe elementary particles, we don't know what. And she died before she could have a Nobel Prize, and other women are still alive, but they never got a Nobel Prize, even if you think they deserved it. So there is a whole discussion in astronomy. Vera Rubin was actually a Jewish lady. She was another of those people who really enjoyed meeting, very nice and modest and ready to talk. And I really had a wonderful impression of her, another inspiring person. So we're going to build very large mirrors now. We're able to build very large mirrors on Earth, and they're being built by Europe and by the United States, in Chile, and hopefully one also in the Northern Hemisphere soon. This is only 8 meters, it's huge, but it will be dedicated to observing explosions in the universe and those sorts of transient and variable events. So it will have a very large field of view, like look at how many moons will fit inside. This is considered very, very large for astronomy. And it will be able to measure very precise positions. Every circle contains 10 million galaxies, so there will certainly be lots of supernovae, novae, gravitational mergers, whatever. And then they will produce a movie, sort of, and make it available to all astronomers in all. I wanted to tell you, and it's another one of these very exciting new facilities that are being built.
Marina, thank you. We will open it up to questions. And the first one that was asked was, and if you could repeat it after I say it.
Sure.
So
Shall I
everyone-
look in the end show and look in the Zoom?
So one of them was, what does the backside of a black hole look like?
Black?
The backside of a black hole.
It will look black. I mean, it doesn't emit radiation in any direction. So I'm not sure what they meant.
And then Rob Golden is asking, I've heard descriptions of the gravity of a black hole that posit that one would break apart because the gravity of one's feet would be so much more powerful than the gravity just a few feet away at one's head. However, if no one force is experienced on a failing object in a gravitational field, an inertial frame of reference, until
Here,
it
can I
hits the
stop in?
mass at the center of the field.
Can
It
I jump
seems
in with
if
that?
one could fall into a black hole, one would really not feel the gravity of a black hole at all until hitting the mass at the center. Is my reasoning correct?
I don't know. First of all, we have to define what it means to feel the gravity. And second of all, we see all stars being disrupted. That's how another Nobel Prize was given, because it led to the discovery of the black hole at the center of the galaxy. So the stars and objects are completely disrupted. They're not solid objects that would be attracted by a black hole. So I don't know. It would be like a dust or strip of gas coming in. So then at that point, what gravity you will feel, there is no center of the object that is put into a black hole.
Any questions from our in-person audience?
Yeah, I got it. Well, I'm trying to come up with a well-phrased question. I didn't realize that you had different elements being created by the mergers or the explosions of these various white dwarfs or other sized stars. Is that the way to think about what the origin of the heavier elements, the metals, even the ones that exist on the Earth and other planetary systems? Is that where the origin of those metals come from?
It depends on which metals. Yes, the question is whether all heavy elements come from merging white dwarfs or merging neutron stars. And the answer is that it depends on which elements. If you have carbon or nitrogen, some of them are, so some of these elements are from the normal stars, and the normal burning, right? So, and that's possibly also why they're very common, the most common elements, up to oxygen. But then some of them can only be formed in merging compact objects. So by compact objects and white dwarf, neutron stars, well, black holes, we don't know, of course. So merging white dwarfs are the main contributor to iron, also other elements, but all the iron is formed in them. And then merging neutron stars are one main contributor to very heavy elements, and you go up the scale in the periodic table. So there is a variety of origins of elements.
So the origin of the metals that are on the Earth or other planetary systems, are they just remnants from various explosions and then sort of swept up by the suns and other solar systems?
Yes, yes. So the origin of many metals that we have on Earth, does it come from the stellar explosions of merging objects? And the answer is yes. Iron practically only from the thermometer supernova. Any other questions? Is there anything else in the chat?
It's difficult to even have the intelligence to compose a question.
No, right. I thought there were more questions.
It's so interesting to hear your description of things that you've heard by the periphery for so long, and then to understand how they relate to each other.
Thank you. Yeah, it's all related, you know, all these fields are all related, so astronomy is a relatively quite a multidisciplinary system. Discipline, I mean.
How somebody who is in your field, how much of your time is actually at a telescope? How much of your time is proposing something for the telescope to do, and how much of your time is looking at data on the field?
So the question is, how much time do we spend at the telescope? How much time do we spend proposing observations or in projects? And how much time we actually spend analyzing data on the computer? It varies from person to person, but of course, most of the time is spent analyzing data at the computer. Optical telescopes, you go just for a few days a year, maybe, if you work with optical telescopes. But now the largest telescopes, you can visit them, but you cannot really do the observations yourself. They're too complex. So there are technicians doing it, and service astronomers doing it for you, the largest telescopes. And then much of the data we acquire is, of course, from space, and you don't go there. There are people who just do all the analysis for you. And then there are different type of scientists in astronomy. There are some who just dedicate their life more to instrumentations, like Rainer Weiss, more of a physicist, but some people just do that, and so they spend a lot of time planning observations and planning the instruments. Some of them are more engineering types. It's becoming more compartmentalized, and there are more engineers working in astronomy, of course, proper engineers. But we spend a lot of time planning observations. So that's about 30–40% of the time of some of us. And the rest of the time is actually data analysis. But then there are people who work only on the models, and they spend very little time on the actual experiments and observations. They spend most of their time just on the computer making models. So there is a lot of computational power in a lot of work. So it's half and half. Anything else? Shall we close it here, or are the people on the Zoom? Okay. Okay.
What are you most excited about now that you're working on?
Oh, we are working on all, so I'm very excited about finding gauging this chemical supernova really well. But everything, I mean, these gravitational wave discoveries are just amazing. Just so exciting. And everything really excites me, but of course I get more passionate about things I work on myself. But it doesn't mean that I'm not admiring what other people do.
Marina, when you travel between UW-Madison and Italy and Israel, for example, are you doing the same work, or are you doing different
I do the same work. There are some different collaborations, but we basically do the same work.
When you were at the Technion, what language were you using?
Hebrew. He wanted, actually, when we give talks, it's usually in English everywhere, but when I talk with my collaborators, it's in Hebrew.
How old were you in the
18, not before. So. But still, I think at 18, you're smarter than at my age, for instance. I cannot learn the language so quickly at my age.
Marina, one of the things we didn't share was also your personal, like your son. Can you tell us something also about Roberto?
So Roberto is my son. He was born in Madison, and he's a neuroscientist, like my friends here. He's doing his PhD. He hopes to be able to finish in a year and a half or something like that. And he's studying serotonin, the effect of serotonin on the developing fetus. That's his thesis. And he lives in Denver, at the Anschutz campus of the Colorado University, the one in Boulder. So, so it's a very interdisciplinary field, even more than astronomy. Thank you.
Thank you, everybody. We will sign off. Gary and Adrian, I'm not sure if you guys wanted to have any closing comments. You might be busy eating.
I want some of the food. Has been promised to me.
Yeah.